Dear students, in the last class, we have explained two-stage least squares. When there is only one endogenous explanatory variable with more than one instrumental variable. Now we consider the cases in which there are more than one endogenous explanatory variable. Now, consider this model. Y1 is equal to theta 0 plus beta 1 y2 plus beta 2 y3 plus beta 3 z1 plus beta 4 z2 plus beta 5 z3 plus u1. Now, in this model, it is assumed that y1 and y2 and y3 are endogenous. We further assume that expected u1 is equal to 0 and also that u1, expected value of u1 z1 equal to expected u1 z2 equal to expected u1 z3 is equal to 0. That is, u1 is not correlated with the z1, z2 and z3. And y2 and y3 are endogenous, so that expected value of y2, u1 not equal to 0, expected value of y3, u1 not equal to 0. That is, y2 and y3 are correlated with the u1. Now, to estimate this model with the two endogenous variables y2 and y3, we require at least two exogenous variables not appearing in this equation but correlated with the y2 and y3, say z4 and z5. In the previous class, there was only one endogenous explanatory variable, y2, with two instruments. Now, we have two endogenous explanatory variables, y2 and y3. So, to estimate this model by using two-stage least squares, we must have at least two exogenous variables not appearing in this equation. Not appearing in this equation. And then from our analysis of a single endogenous explanatory variable, we need either z4 or z5 to appear in each reduced form for y2 and y3. And we can use the F test to test it. Even though it is a necessary condition for identification, that is, z4 and z5 appear in the reduced form for y2 and y3. Even though it is a necessary condition for identification, it is not sufficient. That means, also, although the necessary condition is satisfied Unfortunately, it is not sufficient. The problem is, it is possible that Z4 appear in both. In the two-stage least squares, in the first stage we regress Y2 on Z1, Z2, Z3, Z4 and Z5. Similarly, Y3 is regressed on Z1, Z2, Z3, Z4 and Z5. You will get Y hat 2 and Y hat 3. In the second stage, Y2 and Y3 are replaced by Y hat 2 and Y hat 3. So it is possible that Z4 appear in both and Z5 not appear in either of the reduced forms. Z4 appear in both, Z5 appear in neither. If this is true, we do not have two exogenous variables. We have only one exogenous variable correlated with Y2 and Y3. If Z5 does not appear in either of the reduced form equations, then we have only one exogenous variable Z4 for Y2 and Y3. So, in that case, two-stage least squares will not produce consistent estimators for beta j. Consistent estimators for beta j. So, whenever there are more than one endogenous variable, whenever there are more than one endogenous explanatory variable, identification can fail in many complicated ways. Anyway, we can state the necessary condition for identification when there are more than one endogenous variable. And this necessary condition is known as the order condition. Order condition for identification. Remember this. If there is only one endogenous explanatory variable, one exogenous variable is enough. When there are two endogenous variables, there will be at least two exogenous variables not present in this equation. That is a necessary requirement for identification. Now, the necessary condition for identification, known as order condition, is stated like this. We need at least as many excluded exogenous variables as there are included endogenous explanatory variables in the structural equation. The order condition is we need at least as many excluded exogenous variables as there are included endogenous explanatory variables in the structural equation. This is the order condition. That is, if there is one endogenous explanatory variable, there will be at least one excluded explanatory variable or excluded exogenous variable. If there are two endogenous explanatory variables, there will be at least two excluded exogenous variables. Three like that. This is known as the order condition. This is the easiest way to check identification because this involves only counting the number of endogenous explanatory variables and exogenous variables. This is only a necessary condition. Even if this condition is satisfied, it is not necessary that an equation is identified. A sufficient condition is given as rank condition. Rank condition require the use of matrix algebra. Matrix algebra. Anyway, this is the necessary condition. Let me consider this from a different perspective. While discussing simultaneous equation models, we have discussed the necessary and sufficient condition as order condition and rank condition. The order condition was k minus k greater than or equal to m minus 1. K minus k is the number of predetermined variables excluded. M is the number of endogenous variables. In that equation, minus 1. So if you consider this statement, minus 1 means the dependent variable here. So k minus k, suppose that the excluded variables are 2, greater than or equal to, here m, number of endogenous variables, 3 minus 1. So it becomes equal to 2. So the condition is same. But when we discussed it in the context of simultaneous equation models, it is the traditional approach. Now this is the same condition because it is the same as the order condition and rank condition. The 2SLS that we discuss here is the same as the 2SLS we have discussed there. You just compare this with that explanation. So this is the order condition. At least 2. If there are more than 2, we used to say that the equation is over-identified. Now in the language of IV, instrumental variables, we will say over-identifying restrictions. Over-identifying restrictions, something which we will discuss in a later class. So in the last class, I will summarize what we have discussed so far in the context of instrumental variable methods.